Now let us understand center of mass. Center of mass of system of particles or of a body is the point inside or outside the body where the whole mass of the body can be assumed to be concentrated. Now look at the center of the broomstick and the ball. Now let's take example of two particle system. Take x-axis as the line joining two particles of mass m1 and m2. Let the distance of two particles be x1 and x2 respectively from same origin O. The center of mass C of the system is at distance x from O, where x is given by x equals to m1x1 plus m2x2 upon m1 plus m2. If two particles are of same mass, then m1 equals to m2 equals to m2. Then x equals to mx1 plus mx2 upon m plus m, that is x1 plus x2 by 2. Thus, for two particles of equal masses, the center of mass lies exactly midway between the line joining them. Now, let's take the example of three particle system not lying in a straight line. The particles are of mass m1, m2 and m3 respectively, x1y1, x2y2 and x3y3 on xy plane. The center of mass C of such a system will be located at x, y coordinates. X, y will be defined as x equals to m1x1 plus m2x2 plus m3x3 upon m1 plus m2 plus m3, whereas y equals to m1y1 plus m2y2 plus m3y3 upon m1 plus m2 plus m3. For a particle of equal masses where m equals to m1 equals to m2 equals to m3, we get x equals to m times x1 plus x2 plus x3 upon m plus m plus m, that is x1 plus x2 plus x3 by 3. Similarly, y equals to m y1 plus y2 plus y3 upon m plus m plus m, that is y1 plus y2 plus y3 by 3. Thus, the three particles of equal masses, the center of mass coincides with the centroid of triangle formed by the particles. Result of equation x equals to m1x1 plus m2x2 plus m3x3 upon m1 plus m2 plus m3 and y equals to m1y1 plus m2y2 plus m3y3 upon m1 plus m2 plus m3 are generalized easily to A. System of n particles not necessarily lying in a plane but distributed in space. The center of mass of such a system is at x, y and z, where x equals to sigma mixi by m, y equals to sigma miyi by m and z equals to sigma mizi by m. Here m equals to sigma mi is the total mass of the system. The index I runs from 1 to n. Mi is the mass of ith particle and position of ith particle is given as xi, yi and zi. Equation x equals to sigma mixi by m, y equals to sigma miyi by m and z equals to sigma mizi by m can be combined into one equation using notation of position vectors. Let Ri be the position vector of ith particle and r be the position vector of the center of mass. Ri equals to xi I cap plus yi j cap plus zi k cap and r equals to xi cap plus yj cap plus zk cap. Then r equals to sigma miri by m. A rigid body, such as meter stick or a fly stick, is a system of closely packed particles. Equation x equals to sigma mixi by m, y equals to sigma miyi by m, and z equals to sigma mizi by m, and r equals to sigma mi ri by m are therefore applications to rigid body. The number of particles in such a body is so large that it is impossible to carry out the summation over individual particle in these equations. We subdivide the body into n small elements of mass delta m1, delta m2 and so on up till delta mn. The ith particle delta mi is to be located at point xi, yi, zi. The coordinate of center of mass are then approximately given by x equals to sigma delta mi xi upon sigma delta mi, y equals to sigma delta mi yi upon sigma delta mi, and z equals to sigma delta mi zi upon sigma delta mi. As we make n bigger and bigger and each delta m smaller and smaller, this expression becomes exact. In that case, we denote sum over I by integral. Thus, sigma delta mi tends to integral dm equals to m, sigma delta mi xi tends to integral x dm, sigma delta mi yi tends to integral y dm, and sigma delta mi zi tends to integral z dm. Here, m is the total mass of the body. The coordinates of center of mass now are x equals to 1 by m integral x dm, y equals to 1 by m integral y dm, and z equals to 1 by m integral z dm. The vector expression equivalent to these three scale expression is r equals to 1 by m integral r dm. While calculating the center of mass of homogeneous bodies of regular shape like ring, disc, sphere, rod, etc., by using symmetry consideration, we can easily show that the center of masses of these bodies lies at their geometric center. Let us consider a thin rod whose radius is much smaller than that of its length. Taking the origin to be a geometric center of the rod, x-axis to be along the length of the rod, for every element dm of rod at x, there is an element of same mass dm located at minus x. Thus, the net contribution of every such pair of integral, and hence the integral x dm itself is 0. For equation integral x dm equals to integral y dm equals to integral z dm equals to 0, the point for which the integral itself is 0 is the center of mass.